Hello again. So welcome back. We are continuing our galaxy unit. This is chapter 13. Our What Are We summary is that we are small and proud. So yes, if you're not feeling small yet, you probably should. We live on this little tiny planet Earth on a normal kind of sized sun star. And we're in a galaxy that's just one of billions upon billions of galaxies in our universe. So we are small, but yet being small doesn't really mean that we're not significant, because our little tiny brains can actually understand some of the most profound mysteries in our universe. And so we're going to continue on and take a look at our galaxies, looking at normal and active galaxies. And so we did first, with our study of galaxies, look at our parent galaxy, the Milky Way. We are children of the Milky Way galaxy, and got a look at some of the physical properties, just like what we did with the stars. We were looking at some physical properties of our galaxy, and trying to piece together how the galaxy formed. So we are kind of branching here to other types. We do have similar types to our galaxy, but there are many other types of galaxies. And so a classification system is where we kind of begin here. And they'll also go through physical properties of the various kind of galaxies, and piece together sort of the evolution, our best understanding of the evolution of our galaxies. And so in that sense, let's go ahead and get started. There's lots to cover in this chapter. But like we mentioned last time, less than 100 years ago, astronomers didn't even realize that galaxies existed, that we were living within a galaxy, and that wasn't the only galaxy, that there were billions of other galaxies. And so it really wasn't until about 1920s that we understood that there were other galaxies much like our own, and we will find even quite different from our own. So it's not that long ago that we were able to discover this. And so recent decades, when we finally got some good astronomical telescopes that we could look at the variety, the intricacy and the beauty of the galaxies. And so we're going to try to understand how the galaxies evolved in this chapter. The amount of gas and dust is a critical clue, because you remember those are places where new star formation was happening, so that matter that creates the stars will be important. And also we did start to mention interactions between galaxies, that there could be mergers of galaxies that will definitely affect the evolution of our structures. Okay. So we're going to try to build our theories. We've got to gather then certain data about our galaxies. We're going to need to classify them. We need to have an orderly kind of system to classify our galaxies. We want to look at their basic properties, things like diameter, luminosity, and mass. These are pretty common physical properties that we'll look at. And once we kind of get an idea of those typical properties, we're going to start looking at what theories they have about the origin of our galaxies and their evolution. So what's important with how they have evolved over time, because the universe is very old. And some of the most energetic events in the universe, we've talked about a little bit, the nucleus of a galaxy, the Milky Way galaxy nucleus, and hinted around that, yes, they do believe that there is a black hole at the center of the Milky Way galaxy, and they think that that is probably true for most of our galaxies. But certain galaxies, we will see that they are extremely active, so there is something enormously great amount of energy happening at the centers of those, and of course it's greater than the mere supernova explosions of a star, of say a single star. So tremendous amount of energy coming from some of our galaxies. Remember, they said the Milky Way galaxy was more or less on a starvation diet. so that it's fairly dormant. But some of these are very, very energetic, active galactic nuclei they'll talk about, AGN, or active galactic nuclei. So astronomers classify galaxies according to what's going on with their shapes, and so they've got some broad kind of categories, three kind of main ones, and then some subtle differences between them, but the general classification system is what we'll be taking a look at. So it was kind of developed in the 1920s by Edwin Hubble, who is the namesake for the Hubble telescope, space telescope. And so the system of classification, as I mentioned, it's kind of what we do in science. We want to try to categorize things, put like things in a pile, basically, to sort things. So that's what our classification is kind of stemming from, just our natural curiosity to make sense of our surroundings. So 3 important points to note about galaxy classification. You might get here, this is some dust and clouds from an image that's in infrared, kind of making it have sort of a reddish hue to it. So having dust and things could cause this to kind of have a red hue. Those bright, hot stars, the O and B stars, those would kind of give a blue hue to the galaxy, and so gives you some clues about what's going on inside your galaxy. But many galaxies have no disk, no spiral arms like our Milky Way galaxy does, and almost no gas and dust. And these are called elliptical galaxies. That's our first one here. Elliptical galaxies are ranging from huge giants to small dwarfs, so there's quite a variation in there, but they don't have, as you can see, any spiral arms coming from them. They don't have that definite disk in there as well, and so almost no gas and dust. And so they're not regions where star formation is happening. That's the material that we need for stars, the gas and the dust. So they tend to kind of have a reddish kind of hue to them, but there's a lot of variation in those as well. So very few hot, bright stars in those. Not much gas or dust. Disc-shaped galaxies have spiral arms. They contain the gas and the dust in them, although some, and there are sort of subcategories of these, some don't have a lot of gas and dust, but like this one here, a spiral, you can see the beautiful spiral arms, you can see the definite disk region in it, and those bright, hot O and B stars, those massive stars, kind of giving it a blue hue to it because of their luminosities, and their temperatures are very hot. We also have a little subcategory of our spiral galaxies called a barred spiral galaxy, and so towards the nucleus it's sort of a flattened shape in there like a bar, and so they do call those barred spiral galaxies. Our Milky Way galaxy is a barred spiral galaxy, so not just a spiral galaxy, but it's a special one with a barred spiral galaxy, so a barred kind of structure in it, and so that's Milky Way is a member of a barred spiral galaxy. Okay. So these that are starting with S there, and there's a couple pages in your book that talk about your galaxy classifications, probably a little more in detail on page 300 and 301 in your book, if you need a little more than what's in the PowerPoint. But they are having sort of some little subdivisions, so an SA and an SC. These are variations of your spiral galaxies. Some galaxies are what we call then irregulars, okay? So they are very irregular in shape, but they too tend to have a lot of gas and dust in them, but they're just misshapen. They're just very irregular. They don't have the definite kind of disc and spiral arms like our spirals do. And here we even have a couple distant galaxies kind of crossing in front of a more distant one, giving us an idea that there is an interaction between galaxies, which could be some of the reason of why we're seeing the variations that we see in ours. So our irregulars, they do have both the population 1 stars and population 2 stars, right? So the younger population 1 and the older population 2 stars, so a combination of those, but they don't have any obvious spiral arms to them or a nucleus either, so they're irregular is what they call them. Okay. So proportion of the galaxies of elliptical, spiral, and irregular. So after looking at lots of galaxies, about 70% are the spiral. But again, that could be a result of selection effect, like we saw with our stars, because the spiral ones have those bright O and B stars in them. That makes it easier to see those. So, but about 70% are spiral. Yeah, the hot, bright stars, you can make them easy to see. But among our spiral galaxies, about 2/3 are what we call those barred spiral galaxies, with that sort of elongated nucleus in them, of which the Milky Way is a member. They have concluded, though, that the ellipticals are even more common than the spirals. And then we end up with irregulars making up only about 25% of all of our galaxies. And so there are some variations between these galaxies. They do have kind of different colors, as I was mentioning, the different hues that they might have, depending on what kind of stars are in them. The hot, bright O and B stars, very luminous, are going to give it a blue kind of hue. And then those that don't have so much of that, they're going to give sort of that reddish kind of color to it. So spirals and irregulars have plenty of the young stars, the hot O and B stars, very luminous. So they're kind of giving off the most of the light and giving you that blue tint, as I mentioned. Ellipticals contain very few young stars, and they're not, as luminous, but the ones that are the largest are those red giants. So that ends up kind of giving off a red tint or hue to the elliptical type of galaxies. So the coloration can tell us a little bit of something about what kind of stars they have in them. And so they've done some studies in many different wavelengths. We've got some X-ray wavelengths in here. The Spitzer, if you remember, was an infrared telescope, space telescope. And so they've looked at a bunch of them, trying to categorize and count some regions. And at least 100 billion would be visible from today's kind of telescopes. That's the visible portion, about what we could see. 100 billion, I mean, that's a lot. And there's probably even more out there that we can't quite see. Okay, so this would be kind of visible in here. A tremendous number of galaxies. And so this, from the Goods image here, every little spot you see on there, every object in that image is a galaxy. Some of them do look, you can see the spirals in some of those, but others are irregulars and ellipticals as well. So billions of galaxies in there. So we need to find out how far away they are. Remember that the distance measurement is a very important measurement for us. And so once we know our distance, we can figure out, its size, its luminosity. Those end up being pretty easy to calculate. We had that little relationship that we put up there for you. And then finding their masses, a little bit more difficult, and we introduced that with the mass of the Milky Way, those rotation curves. And so can be done, though, and get their masses. And we've got some quite interesting results from our studies. So now that our distances are getting pretty great in here, we're going to use this distance unit here, a megaparsec. So the parsec we're familiar with, but now we're putting an abbreviation in front of it, megaparsec. And so let's kind of put up the megaparsec for you. This would be equivalent to 3.26 million light years, right? Light years. Or if you wanted that in, we could put it in kilometers if you need it in kilometers. 3 times 10 to the 19 kilometers, very cumbersome number there, right? Or if we wanted that in miles, 2 times 10 to the 19th miles. Okay, so just a few variations, conversions for what a megaparsec is. But now that we are thinking about distances to a galaxy or to many galaxies, yeah, we start to need a very large unit here, and the megaparsec seems to do a very good job for us. So 1 megaparsec equal to a million parsecs is what that is. A million parsecs is 1 megaparsec, or 3.26 million light years, and the various ones in there. So million light years in there. So yeah, distances are found by using standard candles. So we talked about the Cepheid variables. It was kind of the highest rung on our ladder that we have gotten to so far. If you remember that on our extragalactic distance ladder. So what we need to know the luminosity and the diameter, okay, of the stars within there. And we can find a standard candle in a galaxy. So those Cepheid variable stars that we learned about, Henrietta Leavitt helped us with those, and Harlow Shapley kind of calibrated it. We can figure out the distances. And so that's sort of that highest rung on our extragalactic ladder that we've gotten to so far. But we could judge then, and here we go. So they are mentioning the Cepheid variable stars are very reliable standard candles. As we mentioned, the period is related to their luminosity, and we do have that little relationship between, I know I've had it up there before, we'll get it up here one more time, kind of the observed, where you can just look at a photographic plate of some stars and get the apparent brightness, right? The apparent visual brightness. That's just what it looks like to our eyes. And then if we get the luminosity, or perhaps the absolute visual magnitude, right? And with this relationship of distance squared, so the inverse kind of relationship for light, meaning like the farther away it is, the dimmer it is. So that inverse kind of relationship. So this, with that distance in there, we can then estimate some other things about it. The observed here, then you're getting that known. You know this from that relationship of your Cepheid variables here, absolute magnitude or luminosity, to the period in days of that pulsation, where it got bright and then it went dim and it got bright again. So this was all from last lecture, so review that if you're a little rusty on that. But yeah, so by comparing the absolute and apparent magnitudes, we can find its distance. So the apparent and absolute visual magnitude, we can get then, we can then estimate or calculate distance with this little proportionality relationship in there. So that was like the highest rung on our extragalactic distance ladder so far. So that was one method in there. But we get to a point where our Cepheid variables aren't quite even bright enough for us to resolve very well much beyond about 100 million light years or 30 megaparsecs away. And so if we want to look at a little further out, we need something that's even brighter than our Cepheid variable stars in there, so as distance indicators. And so they have come up with some supernova explosions. Remember, those are very, very brilliant, very cataclysmic explosions of the distant stars. And so anytime we can get a glimpse at a supernova explosion that happens to be in a very distant galaxy, well, they're all trying to rush in and examine it, because that way it's like a burning beacon out there that would help us with distance. And so supernova explosions and how they dim over time, this is something that they do use, and it puts the next rung on our distance ladder there, the extragalactic distance ladder. And so type 1a supernova are seen in even more distant galaxies, and so we can measure their apparent brightness at maximum, and then we know how they kind of fade over time, and so we can put together then the relationship with distance then. So they use calibration to build the distance scale, reaching from the nearest galaxies to the most distant visible galaxies. And so they do refer this to this as the distance ladder, which I've been mentioning since way back, but they're just now introducing it here. But of course, each step depends on the one before it. We did mention that as well. So that foundation of the scale rests on understanding the luminosity of our stars, and it ultimately rests on measuring that stellar parallax. So let me pop that. I think I've got it here somewhere. Our extragalactic distance ladder. Try to put this under here real quick. Hopefully we'll still be able to see most of this here. That looking? So, yeah, from Earth-based radar ranging, right? Stellar parallax, so actually observing the stars maybe 6 months apart and look for that parallax shift. The spectroscopic parallax, if you remember that from our spectral classes, and what we can get at, the brightness there, absolute magnitude and luminosity, and then you can get your distance from that. The variable stars, so the work of Harlow Shapley and Henrietta Leavitt, we looked at that last time. So how they get bright and then they dim, those pulsating kind of stars, period luminosity relationship. Tully-Fisher, and they don't really talk about the Tully-Fisher so much in here, but it has to do with the rotational velocity of your galaxy, and then what the widths of your shifts in your spectral lines are. So they don't really go through that one too much, but that is a method of getting at distance as well. But way up there at the top are the supernova, okay, the next rung on the ladder. But looking at, it says L on this axis and time across that axis. I don't know if you can see that too well, but a supernova explosion will get extremely bright, get to its peak brightness, and then it will fade over time and become dimmer and dimmer in a set method. And from this, we can gauge then sort of these standard bombs rather than standard candles, because they are so extremely bright. That helps us to see even farther, give us even further distances. And so that's like the next one up on our ladder for things greater than about 200 megaparsecs to 1 gigaparsec, so even larger distances. This supernova explosion method that they use. And there's actually one more rung up on the ladder, but we'll talk about that in a little bit with the Hubble constant there. But so the distance ladder, this is really the first that they're talking about it, but I've been mentioning it all along. But how the ladder, you know, each distance measurement pretty much relies on the previous step. Okay, that's what they're talking about with that. Okay, and so the most distant visible galaxies are a little over 10 billion light years, so 3,000 megaparsecs away. So that's pretty distant, but that's, again, not as far as they could be, but about the best that we can do. And this is interesting. At such large distances like this, we see an effect similar to time travel, honestly. But when we are looking at a galaxy that's just a few million light years away, we're actually not seeing it now as it is now, but what it was like millions of years ago. Okay, so this is when the light actually began its journey towards Earth. So those very, very distant galaxies, when that light finally arrives to Earth, we are seeing that galaxy or that light like it was millions of years ago. Okay, and so this is a very important kind of concept. It's called the look back time. So when you look at more distant galaxies, you look back into the past by an amount of time called the look back time. So the look back time is basically the time in years that's equal to its distance. Okay, so in light years, and remember, a light year is the amount of time it takes for light to reach the Earth. Okay, that's a light year. It's actually like a distance unit. But yeah, the time in years equal to the distance in light years is known as the look back time. So amount of time it takes for the light from an object to finally reach the Earth, okay? And it is numerically equal to the distance in light years, okay? We use the light year for that. So again, the farther back or greater distance your galaxy is, it's taken millions and millions of years for that light to travel to the Earth. And so we're seeing a galaxy the way it looked millions and millions of years ago, not what it looks like today. Okay, that light hasn't gotten here yet, but from millions and millions of years ago. So sort of like a time travel type of thing. The look back time, very interesting. It actually gives us a glimpse at the universe of those galaxies when they were at a much younger age, what it looked like. And this can help us with evolution as well. So when we look at extremely distant galaxies, we're looking at the universe at a much younger age. And so we can see what things look like at great distances from a much earlier generation in the universe. And so it's a very interesting kind of concept there, the look back time. Okay, so near objects for look back times, not that significant. You know, maybe we're looking at the moon or the sun, you know, that's not too much time for the light to travel from those. To the nearest star is about 4 years for that light to get here, so not too far. The Andromeda galaxy, a little further away from us, that's like our nearest neighbor, Andromeda galaxy, a massive galaxy. 2 million years for that one, and again, a blink in the lifetime of a galaxy. But when we look even to further back, okay, it becomes an appreciable part of the age of the universe. Okay, when you're starting to look back over 10 billion years ago, you know, the estimate for the universe is 13.7 billion years, and so 10 billion years of that, you're looking back far enough that you're looking now at the universe when it was much younger, when galaxies were coming together and forming. So very different in appearance, and that helps us with evolution. So it's a very interesting concept there. But measuring the distance to a galaxy, we have several methods to try to get at it there. But one way to estimate that with a simple relationship, again, the early kind of 20th centuries here, astronomers noticed that the lines in galaxy spectra were shifted slightly toward the longer wavelengths, meaning redshifted. For galaxies really, really far away, that was an even greater redshift kind of thing. So those redshift implied that the galaxies are actually receding from the Earth. This was the first of the thoughts that, and our understanding that, yes, the universe is expanding. So this was some good beginning data for that, evidence for that. But when we're talking about the redshift, so they're looking at the spectrum. Remember how the spectra revolutionized astronomy, and how they get redshifted to longer wavelengths. Okay, so the kind of a Doppler shift thing, moving away from your object, makes it shift to the longer wavelengths. So they call that red, even though we're not just talking about visible light. To longer wavelengths of whatever electromagnetic radiation we have to be talking about, but to longer wavelengths. So that's called a redshift in there. And Edwin Hubble, again, very important in this, in 1929, put together and published a graph here that we have that kind of spelled out that relationship. But it plotted the apparent velocities of recession. So the apparent recession moving away, okay, the speed in kilometers per second, okay, apparent recessional velocity, versus the distance, okay, in megaparsecs, okay, in a very linear kind of relationship to where the slope of this line is known as the Hubble constant, okay. So there is a relationship between apparent velocity of recession and its distance. Okay, and so he put that together in a nice relationship called Hubble law, which is a relationship between recession velocity and distance. So here we can get at distance again. And so he's got kind of a line showing the in the galaxy spectra that are generally shifted toward longer wavelengths, meaning red shifted. And this really was evidence, the beginning evidence, that the universe was expanding. I mentioned that before. And astronomers use this to estimate the distances to galaxies using that relationship, apparent recessional velocity to distance. I don't really think I'm going to write out all of that equation for that, but it definitely does have an equation for that. But this is another one. Actually is the next rung up on our extragalactic distance ladder, which I don't know for sure if you have this one on the handout that I gave you. Okay, but way up there at the top, Hubble's law. So looking at velocity over distance, kind of has that Hubble constant as the slope of that line, useful beyond 100 million parsecs in there, right here a little bit, and so yeah, so some of our most distant objects are calculated with this relationship, the Hubble law in there. Again, we're not going to calculate any of these, but you do have equations for these as well. Recessional velocity and putting in then the Hubble constant in there. You have a math reference card that you could get these from as well. So yeah, even if it's too far away to have the observable standard candles, so like our supernova explosion or our Cepheid variables, knowing your Hubble constant becomes very important. And it's usually possible to obtain a spectrum of a galaxy and able to measure the redshift, so toward longer wavelengths from the spectra. And so this can be calculated quite nicely, but it's very important to know your Hubble constant as precisely as you possibly can. And I believe that, give or take a plus or minus here, The most precise is about 70 kilometers per second per megaparsec, but of course that's within about a 5%, plus or minus kind of thing in there. And so, yes, being able to use that, we can get at distance for even some of our most distant objects. Okay? So very important relationship. So these are apparent velocities. They're making a point here, not true velocities. So we do make sure that these are interpret these as redshifts of the galaxies due to the expansion of the universe. So the fabric, space-time itself, the fabric of the universe is what's doing the expanding, and the galaxies are kind of along for the ride. And so it appears they're getting farther and farther apart. And the more distant ones are receding even faster. Okay? And we'll get to some modern cosmology in chapter 14 where we'll look at that again. But this was the beginnings of coming to the realization that the universe is expanding. So the galaxies aren't getting ripped apart, but the space itself is what's doing the expanding in there. So it's kind of a very exciting thing that Hubble was able to come to the realization of. Expansion of the universe there. So that does allow us to estimate the distance to a galaxy from the redshift in the spectra, the star's spectra. So Hubble law, very important in that. Like our highest rung on our galactic, extragalactic distance ladder in there. Okay. So distance is key to finding diameter and luminosity, right? So luminosity and distance, a key measurement. It's a very important kind of measurement in there. So, yeah. And this is just talking about results of some observations that galaxies differ dramatically in size and luminosity. Your irregular galaxies tend to be pretty small, at least 1 to 25% smaller than our Milky Way galaxy, a little lower luminosity. Even though they're probably our most common ones, they're easy to overlook, so a selection kind of effect that we saw when we were studying our stars as well. Okay. Milky Way is large and it's very luminous compared to most of our spiral galaxies. Some that are even more luminous than ours. The elliptical galaxies cover a wide range of diameters, and their luminosities will change if you remember the diameters and how that goes into the calculation for luminosity. The surface area. So we need the radius of our object, right? That's half your diameter, and you can get at the surface area. That's part of the luminosity calculation in there. So, cover a wide range of diameters and luminosities for our ellipticals. The largest, called the giant ellipticals, are 5 times the size of the Milky Way. In there, you also can find some dwarf ellipticals, so they do vary quite a bit. So there's quite a range with sizes, with luminosities. So there's a great family of galaxies out there that there are so different, and we've got to try to pull together something that would help us to understand why we see so many differences between kind of our galaxies in there. So diameter and luminosity really doesn't determine the galaxy type, right, that we were seeing. So small galaxies are irregular. There's also some small ones that are elliptical. Some large spirals, but there are some large ellipticals as well. So there's got to be some other factors that are influencing the origin and the evolution of our stars. And we already kind of mentioned the merger idea, capturing other galaxies, kind of the hitchhiker galaxies, the interactions between galaxies can really have an effect on them. And so that's sort of evolution we'll look at here in just a bit. But getting at the masses, and so we were looking at how we got at the mass of the Milky Way galaxy last time, and that was that rotation curve method And so, yes, you were looking at sort of what was going on with the wavelength along blue shifted half of the line, right? And red shifted half of the line. So as it sort of rotates, it's coming toward or away. So we're getting sort of some Doppler shifts toward or away the object, the observer. And you can see those in the spectra, right? So here we've got one moving off this way to shorter wavelengths. They call that a blue shift. And this one's moving off towards longer wavelengths. That's a red shift away from the observer. Blue shifts toward the observer. So this rotation kind of curve method, they call that. But that's going to give us some clues into the mass of our galaxy. And with those calculations you can do with that, you do need the true sizes of the orbits of the stars, or maybe even a gas cloud within the galaxy, which of course requires knowing the distance. So that distance measurement becomes very important. So the orbital speeds of the stars are measured as the Doppler shifts toward or away because of the spectral lines in their spectra. And that's enough information to use Kepler's third law. Remember that one? A cubed over p squared, the sum of the masses kind of thing. So that equation, again, that we gave you before, for the mass of the part of the galaxy that's contained in it. And we can end up getting mass for that little region in there, okay? We did that with the Milky Way galaxy. We were looking at that as well. But galaxies that are near enough to be well resolved in there, most distant galaxies appear so small that they can't quite get their radial velocity. So they've got to use maybe some less precise methods, but they'll try to get at their masses. But the masses of the galaxies do cover pretty wide ranges in here. Smallest, if we use the Milky Way galaxy as our reference, as we do, 10 to the minus 6 as much mass as the Milky Way. Some of them, the smallest, do. But you've got some much larger ones that maybe 50 times the mass of our Milky Way galaxy. And so a broad range of masses for our galaxies. So given size and luminosity of a galaxy, we can make a rough guess on what that mass should be. Because remember luminosity, there was another relationship with luminosity. Keep writing equations down. Remember that one? Mass to the 3.5. So if you know your luminosity, then you can get at mass with that little equation in there. But yeah, so trying to estimate that. And recall this also, that when they measure those masses of the galaxies, you remember this? That they find that the measured masses are much larger than expected from their luminosities. They got their luminosities, so the visible light coming off of there, the luminous portion of the galaxy, but there seems to be even much more mass in there. And if you remember, we introduced to you that term dark matter. So what could be making up all that extra mass that the luminosity is not accounting for in our relationship here? The dark matter. And there could be actually quite a bit of dark matter out there, a lot more. So Vera Rubin, in the 1960s, she realized that this was true for most of the galaxies out there that she was studying, most of our nearby galaxies. Measured masses of the galaxies amount to 10 to even maybe sometimes 100 times more mass than what we could actually visualize. Okay, and so they were kind of calling this non-luminous, extremely low luminosity to these, to the point that they were non-luminous. So at first they're thinking, well, maybe this dark matter, as they call it, consisted of some very low luminosity white dwarfs. Remember those? Pretty faint. And maybe some of those brown dwarfs, right? But that still didn't add up. That wasn't enough. So it didn't seem that that was even going to be enough to make up that missing mass, that mass that was non-luminous. Okay, and so it's not well understood what this non-luminous matter is, but we know it's there because of the way it affects gravity. Okay, because it's there. Okay, so maybe interactions here would produce some X-rays that would make it easier to detect. But we were really trying to figure out this dark matter idea. There must be some other undiscovered form of matter in the universe that's detectable only by its gravitational field. And so right now we call that dark matter. To the point that we think that there's about 95% of dark matter in the universe, this non-luminous kind of matter in there. So it does remain one of the fundamental problems that we have in astronomy, but it does appear to be real. We just don't have a handle on it exactly. And in chapter 14, we'll look a little closer at it. But it does reveal that 90 to 95% of the matter in the universe is this dark matter, this non-luminous matter. So not like normal matter where we can get a spectra from it and examine it. So non-luminous. So how can you study something that's non-luminous? Well, the effects that it has on gravity is about the only way we can study that. So it's really the only way to detect it. It's by its gravitational field, but about 95% of the universe is dark matter. Very interesting. Okay. All right, so now we want to look at the supermassive holes in galaxies. And so we mentioned the one in our own Milky Way galaxy at the center of it, lying towards, the direction of Sagittarius on the sky. A very intense radio wave energy source, crowded with stars right around it, right? A very compact object there at the center of the galaxy, the Milky Way galaxy, with the stars just really moving very rapidly kind of around it. But we did mention that the Milky Way galaxy is rather dormant. Every now and then maybe it will get a little trickle of a star that comes by or something, but pretty much on a starvation diet in there. But Doppler shifts measurements show that stars near the centers of many other galaxies, not just the Milky Way galaxy, they're orbiting very, very rapidly. To be able to hold your stars on such small, short period orbits, the centers of the galaxies need to be extremely massive. And so 1 million to a few billion solar masses in a very small area. That's a black hole, okay? And it's a supermassive black hole. So yet no object is visible, right? Light cannot escape from the black hole. So it seems to require that the nuclei of galaxies contain those supermassive black holes. Milky Way has one as well, and that this is actually probably pretty typical for our galaxies to contain the black holes. Okay, and again, that misconception that is going along and just going to suck up everything in its sight, that they're controlled by that black hole. That's not true. Remember how you've got to get close enough to it, sort of thing. And so that mass that's just right around the black hole, well, that's not the whole mass of this enormous galaxy, right? So most of that mass is going to be in the outer part of the galaxy, and just maybe 0.001%, right around the black hole. So it's not like it's controlling everything in the galaxy, sort of thing. Okay, in there. So trying to build a theory that explains the evolution of our galaxies. We're trying to develop that with our Milky Way galaxy, that kind of monolithic collapse theory, and then we modified that just a little bit to include kind of mergers and hitchhikers of other interacting kind of galaxies in the formation of our Milky Way kind of galaxy. So we can probably presume that other galaxies formed in this similar manner. So why the difference between them so much? Why did we have some spiral, some elliptical, some irregular galaxies? What was going on? And it really does seem to be this idea of how the galaxies are clustering together, our superclusters, clusters of galaxies. What's going on with their environment, their surroundings, their neighborhood? You know, what else is out there interacting with it? Okay. And so we look at these galaxy kind of clusters out there, our superclusters. So they could range from few to thousands in a cluster. And so we talk about rich clusters and poor clusters, but that clustering of the galaxy can really help us understand the evolution of our galaxies. What was going on in the neighborhood around our galaxies? And that'll help us kind of understand their evolution. And so this first one here, they're talking about rich galaxy clusters. So these are ones that are going to contain over 1,000 galaxies in them, mostly ellipticals, often giant ellipticals in them, crowded kind of quite densely, and they're kind of put into a volume of 3 megaparsecs or 10 to the 17th light years. Okay, so fairly compacted in there, quite densely compacted in our rich galaxy clusters. And they give us an example of the Coma cluster off in the direction of the constellation Coma Berenices. At least 1,000 galaxies. Most of them are elliptical and type S0. And so these are spiral galaxies that don't have the spiral arms. That's kind of a strange one, but there are categories and subcategories of these. Closer into its center, there's a giant elliptical galaxy and also large spiral galaxies. So pretty compacted area in there. That would be a rich cluster. One or more giant ellipticals at their centers. In contrast, a poor galaxy cluster that they talk about here, fewer than 1,000 galaxies. We've got the irregularly shaped ones. They're less crowded towards the center. So we call those a poor galaxy cluster. Of course, our Milky Way galaxy is in a poor galaxy cluster. Okay. And our particular little neighborhood, which includes the Milky Way galaxy, is called the local group. This is a poor galaxy cluster called the local group. This is our neighborhood where the Milky Way resides. And so we do have the Milky Way galaxy here. And then you can see several different types in here, a few dozen members kind of scattered around. And in a volume that's not much more than 1 megaparsec in diameter. So definitely a poor kind of a cluster. We've got brighter galaxies, 14 are elliptical, 3 are spiral, including the barred spiral galaxy of the Milky Way, and 4 are irregular. And so you probably can't see that too well, but it's interesting to take a look at it, seeing what, the small Mangelic Cloud, the large Mangelic Cloud, those are irregulars. You've got some spirals in there. Where's our neighbor? The large Andromeda galaxy is another spiral galaxy out there. And then just little ellipticals as well, Canis Major dwarf in there. So just a nice little mix, a variety that we have, but this is called the local group. That's what the Milky Way is in. It's the neighborhood for the Milky Way in there. And it's a poor galaxy cluster. A good example of that. But that's very important in determining sort of the evolution of your galaxies, what you've got going on in your neighborhood or your local group in here, because it does show those observations of how those interactions are going to affect the evolution. So clusters as either rich or poor will reveal some fascinating kind of evolution of our galaxies. Rich clusters tend to contain 80 to 90% of the elliptical galaxies and very few spirals. So it almost seems like the more crowded and the more interaction that you have, okay, that's probably going to be stripping your spiral arms and disrupting the spiral arms in there, probably using up your gas and dust and creating a lot of those ellipticals, okay, in there. The more interactions you have, that's a clue to the evolution. Poor clusters, on the other hand, had a larger percentage of spirals, so maybe there weren't quite as many interactions with other galaxies in there. And so among isolated galaxies that are not in rich clusters, 80 to 90% are spirals. So it seems like the spirals, if they're given enough room and not really interacting with other galaxies, can keep the beautiful spiral arms with it. It seems like the more they interact, that disrupts the spiral kind of shape that we have. So that environment is very important in determining what the structure of our galaxies are going to be. And I don't know if I don't know how much they're going to go through here, but you've got a page that really takes you through the interacting galaxies here. Okay, let's see. Well, they do a little bit, but there's a couple pages called Interacting Galaxies, 308 and 309 in your textbook, that has several terms in it that you'll want to be familiar with. I believe it is a bullet on your handout that you want to really take some time and look at those pages in there. But the galaxies colliding and interacting and merging, they have caught some images of that, and that these collisions among galaxies probably, more than likely, are dominating their evolution, why we're seeing the ellipticals and why we're seeing irregulars and then the spirals. So galaxies should bump into one another fairly often, and then especially if you've got your rich galaxy clusters, they'll probably really have lots of interactions. Here's one where we've got, they're called the mice, because it kind of looks like mice, but it's a pair of galaxies that are actually whipping around one another and being distorted. These sort of tidal tails, you can see kind of tidal tails coming from that. So because of the kind of interaction between them, as they pass kind of near one another, they're pulling like streamers of stars and gas and dust away from the galaxies in there. So that's called tidal tails. Again, these terms are on those 2 pages in your book. And then galactic cannibalism is another term on those pages. Sounds kind of awful, but it really just indicates the merging or the interaction of galaxies to where they can kind of consume and merge one another, but they call that galactic cannibalism. It's a term that's in your 2 pages in your book in there, Interacting Galaxies. There's a merging of galaxies, though, on that. And then ring galaxies was another one that they talk about. So here's our tidal tails there, that the interacting galaxies can distort each other with tides, producing those little tidal tails kind of streaming off from them. So they may even trigger the formation of spiral arms. Could be something. Large galaxies can even absorb smaller galaxies. So sort of the galactic cannibalism term that we refer to. Here's another interaction, the antennae on that. You can see kind of streamers coming from those 2. Definitely we have images of interactions happening with our galaxies. So it does happen, it does occur. Um, some of these have multiple nuclei in them. Okay, so that does indicate that there were some mergers of some galaxies, and why we're seeing the multiple nuclei within a larger galaxy in there. So smaller galaxies have been absorbed and just only partially kind of digested at this point. Where the image is with the multiple kind of nuclei within that one. So that does make good sense there. And then the beautiful ring galaxies. So this is where one galaxy pretty much just went high speed kind of through the center of another galaxy. And so this one's called the Black Eye galaxy, quite beautiful in there, but sort of left a bullseye kind of a ring. They call it a ring galaxy because of a high-speed collision pretty much going perpendicular through the center part, the disk part of a galaxy. So that's a ring galaxy. Again, another term that's on those 2 pages in your book. Worth your time looking at those terms, I would say. Okay. So lots of evidence that there are mergers of galaxies. So Milky Way is a cannibal galaxy, snacking on the little, Magellanic clouds. Those were those little ones close to us. And then tides are pulling apart Sagittarius and Canis Major dwarf galaxies. So yeah, certainly our galaxy has dined on other small galaxies in the past. And so it makes good sense that this is very much part of the evolution of our galaxies and why we're seeing the variation that we see in the different shapes and the amounts of gas and dust, young stars, old stars, hot, bright stars. The interactions become very important in the evolution of our galaxies. So they do put this to the test, some evidence with theory, kind of putting together to tell the history of our galaxies, so the objects we want to study here. And so here, just a couple decades ago, this would have been impossible to try to put together the origin and the evolution of our galaxies. But now we've got, our very nice and strong space telescopes that we didn't have earlier on. Combined with advances in computer modeling to crunch our numbers. So theory can allow astronomers to kind of outline the story of the galaxies, kind of their origin and their evolution. And so they do look at some of these, elliptical galaxies appearing to be a product of galaxy mergers, right? So they've kind of been stripped of their gas and their dust sort of thing, triggered star formation, and it just kind of used up all their gas and dust. And so that does make good sense for these mergers. The starburst galaxies are very luminous. Collision has triggered the burst of star formation. Remember how, you need some sort of a shock wave that could definitely trigger some star formation. So some nice pictures there that they've got for us. And then the antennae, mergers and the streamers, the tidal tails coming off of there as well. So lots and lots of pictures to back up this theory that they have. Spirals, though, with the beautiful spiral arms, seem to pretty much be intact. They don't seem to have suffered major collisions. So yeah, when they do interact, you could just imagine how those spiral arms would, since they're so delicate, would be destroyed by the tidal forces with collisions with other massive galaxies. And so they seem to, never really have merged or had major kind of interaction with another galaxy. And so it looks like our Milky Way galaxy evidently has never really merged with another very, very large galaxy. However, we did see that it had a very large Andromeda galaxy out there, another spiral neighbor out there that seems to have cannibalized on some smaller galaxies. Okay, so trying to kind of bring this all together. The barred spiral galaxies may be a product of tidal interaction, so kind of elongating the centers like our Milky Way galaxy. So again, lots and lots of evidence of this interactions that happen. So the barred spiral, okay, result of interaction with its two Magellanic cloud companions, the large and the small. Little interactions going on there, okay, creating the barred spiral in there. Okay, let's see. So some of the ellipticals out there lost a lot of their gas and their dust, as we mentioned. Probably had a lot of interaction that could strip away that gas and that dust. So they're showing the coma cluster, okay, with that one. Okay, let's see. So looking with the largest and most sophisticated telescopes, so we are looking back, our look back time. We are looking at an age of the universe at a much younger time, so we can, in essence, travel back in time. When we are looking at such great distances, that look back time is so large that we do see the universe soon after they had formed. And so when we kind of look at this with these observations, it was showing that there were more spirals and fewer ellipticals, which makes pretty good sense. The spirals that formed hadn't really interacted too much to become ellipticals, right? And so fewer ellipticals in there. And so some of the data here, about 33% of all distant galaxies are in close pairs. About 7% of nearby galaxies are in pairs. So it did seem like a little more interaction, more crowded together early in the universe's evolution of galaxies. So this evidence clearly supports the hypotheses that galaxies have evolved by the mergers, okay, interactions between them. So lots of good evidence for that. So it's very clear. And galaxy evolution is starting to come together with some theoretical versus now we have some observational with our new telescopes out there. So now we want to look at the centers, so the nuclei of what we call active galaxies, active galactic nuclei, and these things that we call quasars, which are some of the most distant objects in the universe, really large look-back times, but very powerful energy sources in these active galactic nuclei. Remember how the Milky Way was sort of dormant, not a lot going on, starvation diet kind of thing. But there are some that we call these active galactic nuclei. So looking far away, back in time, astronomers have discovered the origin of active galaxy energy sources, or these outbursts, being very closely related to the formation and the history of galaxies. And so this first type of active galaxy was discovered in the 1950s. And they were named radio galaxies because they were sources of very, very strong radio. Okay, and so radio wavelengths, very active. And so they end up calling these just a flood of energy coming out of them, active galactic nuclei, or AGN for abbreviation in there. And so Carl Seifert, in trying to kind of categorize these, he named for him, called the Seifert galaxies. He noted about 2% of spirals have small, highly luminous bulges at their centers, so luminous nuclei, and he referred to them as Seifert galaxies. Spiral galaxies, highly luminous nuclei in their bulges, and that's sort of his category, and that he called them. They had some other types that they're kind of going to talk about. I'm going to go through that a little bit. But these Seyfert nuclei are 3 times more common in interacting pairs of galaxy, as you could imagine. So the more interactions they have, that is going to feed the supermassive black hole at the center. And so all that material entering the black hole is going to create a lot of activity. Why we're getting the radio signals in there. So having a companion in there is certainly a good reason that we would see these being active. Okay, and there was another one in here, the double-lobed radio sources in here, where you could almost get, you know, excited gas emerging from 2 directions from the lobe. So sort of a lobe looking, so double lobed radio, inflated by these jets of excited gas kind of emerging off in 2 directions of your galaxy. Kind of interesting to see those. But they're, again, associated with interacting galaxies on there. So they do seem to be related. The active galactic nuclei, or AGN, seem to be related to that matter falling into that central black hole via an accretion disk around it. And so very hot, stars are moving very rapidly around that black hole, and so rays are coming out from this, jets of excited gas, right, from that region. So these double-lobed radio sources is another type of this matter falling into the black hole. So having another galaxy to interact with is what's keeping these so active. And so that's just sort of showing these sort of double-lobed excited jets of gas flowing from both regions of the galaxy as a double-lobed kind of radio source. Okay. Then these quasars are another one that we talk about. They call them quasi-stellar objects, and so they put that word together, quasar, quasi-stellar objects, quasars. So QSOs. But these are extreme examples of active galactic nuclei. The quasi-stellar is, they thought their spectra resembled stars, but these are not stars at all. They are very, very active galaxy nuclei in there. So, and these are very, very distant, some of the most distant objects in the universe. And so when you can look at these, you are looking back into the past, the universe's past, several billion years, tens of billions years in there, a good 10 billion years for this. So quasars are just kind of like extreme examples of active galactic nuclei in there. Okay, so they must be very, very great distances, because they do exhibit very large redshifts. So these are evidently so far away. These are some of the most distant objects that we have. They're easily photographed, and they're quite bright. They have 10 to 1,000 times the luminosity of a large galaxy, so they're ultra kind of luminous. They're kind of ultra active in there. The most luminous, located in very distant galaxies. So they do stand as a nice beacon to help us with some of our distances as well, some of the most distant objects. Okay, let's see. Let's take a look at a search for a unified model for our active galactic nuclei and our quasars. And so they have put together a model, and they kind of name these active galactic nuclei and quasars, and there's things called blazars as well. Depending on how we are looking at the black hole and the accretion disk around the black hole, and then there's like this dense cloud of dust and gas around, sort of molecular dust and gas around it. So I've got my little galaxy here to kind of help us with this, but it all kind of centers around the supermassive black hole surrounded by an accretion disk, and then sort of this torus or donut shaped kind of dense disks of gas and dust around it. So yeah, we've got matter in an accretion disk that can get very close to the black hole. Because that's so massive, the supermassive black hole, your orbits of your stars and your material is going to orbit very fast around it and get even hotter and hotter and create an accretion disk around it. And so kind of immediately around the black hole, it's kind of puffed up. It's thick enough to hide the central black hole from some viewing angle. So depending on how we're viewing, okay, however the galaxy happens to be tilted toward us, are we looking edge on? Are we tilted a little bit so that we can get some of that gas and dust and a little bit of the accretion disk? Or are we tipped to where we are looking straight down the black hole, kind of down the dragon's mouth kind of thing? So what is the position of our model, okay, as what's described in each of these, in how we view the black hole and accretion disk? Is what it kind of talks about in there. So, and the way you're viewing it, the amount of light and the spectral lines that you're going to see in your spectra are going to be a little bit different. And so we do have kind of a variety of lines that they're going to talk about. But this is sort of the basic idea. I don't know how well you're going to see that. But right in the center, there's the black hole. Then there's this accretion disk around it. Right, and then there's sort of that torus of the dense disk of gas and dust in that region, that torus they call it, kind of a donut shape. Yeah, donut shape of dusty kind of gas, and it's a little cooler in that region. The accretion disk is, of course, very hot near we get to the black hole in there, and so again, the spectra will vary just a little bit. So depending on your view. So this first one here, if your view is edge on, okay, so we've got our little edge on from the edge. You can't see the central zone from that view. The dusty torus ends up blocking your view of that. So you see radiation emitted above and below, right, the central disk. And it's relatively cool, that dense kind of dusty torus in there, cooler. Okay, a little bit. So you're going to see some narrow kind of spectral lines coming from that region in there. So depending on, you know, how it's tilted, it will affect our spectral lines that we happen to see. Okay, so that's one view. And we're thinking, you know, emitted from the gas moving above and below. These are probably the radio galaxies. I have a summary chart somewhere, if I can find it, that we'll put up here in just a second. The radio galaxy in there, like a Seifert galaxy. Then let's say we tip it just a little bit. So we're seeing a little bit of that accretion disk in this one. So if that accretion disk is tipped just slightly, you might be able to see some of that very hot gas and really rapidly moving objects near the center of that cavity. So we've got a broad line emission because that gas is so hot and moving so rapidly. It broadens our emission lines for that. And this one is what we would call the quasars. Okay, the quasars, where you're getting very hot, very luminous objects coming from that, very high velocities. for that. So your spectral lines will spread out just a little bit so they can look at the spectra and kind of get an idea. And the third way is if you are looking directly down the central cavity and the black hole, so down the dragon's throat, they say here, we see a jet emerging perpendicular to the accretion disk. So here's the accretion disk, perpendicular to the accretion disk, like straight at us. So it results in a very bright and highly variable source with few or no emission lines. So if they see that direction, then this is known as what we call a blazar. Okay, so a blazar, very luminous, highly variable source, and is known as a blazar because it's pointed directly down the black hole, the central kind of cavity. And so this is sort of a unified model to try to explain these active galactic nuclei, the quasars, and now we've introduced blazars to you. So, very high speeds, relativistic gases in the sense that they're almost traveling the speed of light in there, and it's pointed directly toward our line of sight in there. Let me find my summary. If I have it, let's see where I put it. Here it is. That kind of summarizes what we were just talking about, the various. So here's the example. I've got a little handout there that shows the three viewpoints. So edge on, tilted slightly, and then right down the dragon's throat, so to speak. And so when you do see that, to where we're looking above and below, so kind of edge on, that's where we would see our radio kind of galaxies, our Seyfert galaxies. They kind of have them in different categories, Seyfert 1, Seyfert 2 galaxies, but those radio kind of galaxies in that region, okay? Broad line kind of spectra in there. Narrow line for that one. And then when you get here towards the accretion disk, so it would be tilted slightly. Now we can see a little bit of that accretion disk. You're getting the broad line region, and that would be where we would see our quasars, right? So the quasar, the observer would see that quasar, very luminous region because it's very hot around that accretion disk. And then when it's tilted, perpendicular to the accretion disk, pointing straight at us like this viewpoint, the observer sees the blazar, okay? So that's just a summary of, the three different kind of directions. Trying to put together a unified model of looking at these active galactic nuclei. A nice little diagram that I think kind of pulls that together just a little bit. Okay. So yes, they have lots of little examples of this, really trying to pull it together to get a unified model for it, and that's what they've come up with, and it does tend to explain these variations of these active galactic nuclei. Evidence is accumulating that most of the galaxies seem to contain a supermassive black hole at their center. Even the Milky Way, right, and the nearby Andromeda galaxies contain these central black holes. So it seems like it's something that's pretty common, but only a few percent of them are the active galactic nuclei. So that must mean most of the supermassive black holes are pretty much dormant or kind of on a starvation diet. They're not being fed very large amounts of matter. Just, a little slow trickle flowing into could explain kind of some mild activity seen there. Takes a lot more to trigger and to make an active galactic nuclei. So mergers, interactions between other galaxies can certainly twist them, rip tidal tails apart. So active galaxies are often very distorted looking, so that's further evidence that they're the tidal forces of interacting and merging galaxies that's further evidence for that. And so those interactions can throw stars, clouds of interstellar gas and dust in towards their centers, and that will flare up, and you will get the active kind of galactic nuclei. I think they've got a series of pictures here where we've got a star, right, drifting near a supermassive black hole, and you can kind of see how the star is flung away from the black hole, but a little bit of that does kind of fall into and form an accretion disk around, and that you can't see that probably very well, but it's a black circle. It's a black hole right there, and then a little accretion disk around it. So yeah, the interactions could kind of keep kind of an active galactic nuclei going, powered by that supermassive black hole at the center. So yes, seems to be a galaxy forms its nuclear bulge, a certain fraction of that mass kind of sinks towards the center, and this supermassive black hole is kind of forming as the galaxy kind of forms in there. And so of course any matter kind of falling in there is going to create and trigger a violent eruption and keeping these going and active. And so we will learn that the universe began 13.7 billion years ago. And so as we mentioned, some of those quasars, those very active galactic nuclei, are over 10 billion light years away. So their distances are very, very large, to the point, right, that they appear as they were when the universe was only 10% of its present age. I mean, it was a young universe then, when we had these active galactic kind of nuclei back then. So when we look at that, we are in essence looking back at how the universe appeared billions of years ago, 10 billion years ago. And so it seems that galaxies were closer together back then when the universe was young. And keep in mind, we already kind of mentioned that the universe is expanding. And so at that time, 10 billion years ago, the universe was actually closer together. It hadn't expanded very much. The fabric, space-time hadn't expanded very much. So they were closer together. Those forming galaxies had an opportunity to collide more often. And so we just saw how those collisions between the galaxies could throw matter into the supermassive black hole and trigger eruptions. And so why we're seeing these active galactic nuclei farther back in time, earlier part of the universe, makes good sense. Things were crowded back then. So it really does kind of help us with setting up an evolution of our galaxy formation. So we'd be looking back at an age when they were actively forming, colliding, and merging. So the age of the quasars they were 1,000 times more common than they are now, okay, as the universe has kind of continued to expand, sort of thing. Then they take it a little further. If you looked back to even higher redshifts, so even farther distances, you would see fewer quasars. Well, you are looking back at an age in the universe that it was so young that the galaxies haven't even had a chance to form yet, okay? And so, you don't have your quasars because it didn't have the galaxies interacting with one another. And so this is just fascinating how we can put together kind of an evolution using these quasars, these active galactic nuclei, and use them kind of as a time machine, pretty much. So nearly all the galaxies contain supermassive black holes. Those black holes may have suffered quasars, right? Eruptions when the universe was younger. The galaxies were closer together, and the infalling gas and dust were more plentiful. That's probably a good idea why we see those so far away and not so much closer up, meaning distances and meaning more modern time, okay, in the universe. So it's a very good example in there. And they're speculating here that our own Milky Way is a good example. It might have started out as a quasar long ago, but now that it's kind of got not so crowded in its neighborhood, its supermassive black hole is resting. But they can be reawakened anytime you get a merger or interaction. And we've got some neighbors out there that it could become an active galactic nucleus once again in there. So it really does help us with the evolution by studying these very interesting active galactic nuclei, the quasars, in there. So that is the galaxies, the normal, and then these active galactic nuclei that chapter 13 took us through. And so in chapter 14, which is kind of part of this unit, it's going to take us through sort of modern cosmology, our modern thoughts and ways of thinking about the origin of the universe as a whole, and maybe where the universe is going to be going in the future. And so it's got some interesting things in it. So again, we're going to continue to kind of branch out, and now next we will be studying the universe as a whole. So we've made our way from studying from our perspective here on planet Earth, and moved our way out to the sun, and then the family of stars, and then our Milky Way galaxy, and then all this universe full of galaxies. And now we want to study the universe as a whole. So cosmology will be our next topic in chapter 14. So I will see you very soon. Thanks.